On October 29th, 2025, 3i Atlas reached perihelion and broke every law we thought we knew. It brightened when it should have dimmed. It changed colour, from icy green to steel blue. Then it turned and began to move away, accelerating without thrust. No jets, no dust, just motion, calm, deliberate, intelligent. And somewhere near Mars, weeks earlier, a faint whisper was caught at 1.4 gigahertz, the hydrogen line, the frequency of life, a frequency no natural process should echo so precisely. Coincidence, or communication? And now, with many explanations growing increasingly improbable, only two remain. Either 3i Atlas is the most statistically impossible accident in the history of the cosmos, or it's something else entirely, something designed, guided, and now revealing itself. And if it's the second one, then the question isn't what it is, it's what it does next. Stay with me until the end, because tonight you'll discover why some scientists now believe that what's coming next has already begun, and why the next chapter of this story may happen right above our heads. If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think about this new development. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The anomaly unfolds. The universe doesn't usually break its own rules. When it does, we notice. On October 29th, 2025, something happened that shouldn't have been possible. An object designated 3i Atlas, the third confirmed interstellar visitor to our solar system, reached its closest point to the Sun. Scientists call this moment perihelion. For comets, this is usually the grand finale. They blaze bright, shed their guts in spectacular tails of dust and gas, then fade as they coast back into the darkness. It's predictable, it's physics, it's what always happens, except this time it didn't. Instead of dimming after perihelion, 3i Atlas got brighter. Instead of the expected reddish hue from dust reflecting sunlight, it turned blue, and instead of following the clean, predictable arc that gravity should have imposed on it, the object appeared to accelerate. Not drift, not coast, accelerate. The numbers that started coming back from observatories around the world were frankly disturbing. Researchers reported a non-gravitational acceleration of approximately 0.02 millimeters per second squared. That might not sound like much, but for an object hundreds of millions of miles away, moving at interstellar speeds, it's huge. It's the difference between a rock tumbling through space and something with a steering wheel. Then came the positional data. The Atacama Large Millimeter Array, one of the most precise astronomical instruments on Earth, reportedly found the object roughly 4 arcseconds off from where it should have been. 4 arcseconds translates to tens of millions of miles in actual spatial terms. You don't drift that far by accident. You don't end up 4 arcseconds away from your predicted position because of a little outgassing or a computational error. You end up there because something changed your course. Now here's where this gets uncomfortable. In all of astronomy, when we observe an object doing something unexpected, we have a toolkit of explanations. Comets outgas, asteroids tumble, gravitational interactions nudge trajectories, solar radiation pressure pushes lightweight objects around. We've seen it all before, and we can model it with exquisite precision. But 3i Atlas isn't playing by those rules. The acceleration is too strong, the colour change is too weird, the trajectory deviation is too precise. So we're left with exactly 2 possibilities, and both of them are absolutely wild. The first possibility is that this is the most improbably rare natural event in the history of observational astronomy. An interstellar object with chemistry we've never seen, structure we've never imagined, and behaviour that somehow mimics intelligent guidance through sheer cosmic coincidence. A 1 in a trillion accident of nature that just happens to look exactly like something deliberate. The second possibility is that 3i Atlas is not natural at all, that it's artificial, engineered, built. That we're watching, in real time, as an intelligently guided object moves through our solar system, adjusts its trajectory with precision, and perhaps, just perhaps, reveals itself as it approaches Earth. I want you to sit with that for a moment, Really sit with it, because if the second possibility is true, then everything changes. Every assumption we've made about our place in the universe, every confident declaration that we're alone, or that interstellar travel is impossible, every smug dismissal of the question, are we being visited, all of it crumbles. And it crumbles not because of a blurry photograph or an anonymous whistleblower, but because of hard data from the most sophisticated instruments humanity has ever built. But we're getting ahead of ourselves. Before we can seriously entertain the artificial hypothesis, we need to understand just how strange this object really is. We need to look at the observations, the measurements, the weird little details that don't quite add up. We need to see why the natural explanation, which should always be our first choice, is starting to look increasingly strained. And we need to talk about the radio signals, because here's something that hasn't made it into most mainstream coverage yet. On October 3rd, 2025, roughly 3 weeks before Perihelion, reports emerged of radio emissions detected near Mars at 1.4 GHz. That's the hydrogen line, the universal frequency that every civilization capable of radio astronomy would recognize. The frequency that SETI researchers have been monitoring for decades, because if anyone out there wanted to say hello, that's the frequency they'd use. The timing is haunting. 3I Atlas was crossing near Mars's orbital plane on October 3rd. The Perihelion event happened October 29th. That's 26 days later. Then, on December 19th, 51 days after Perihelion, the object makes its closest approach to Earth. These aren't random intervals. They're the kind of precisely spaced events that make you wonder if someone, or something, is following a schedule. Now, I need to be clear here. The radio ping claim is unverified. No major observatory has publicly confirmed it. NASA hasn't released a statement. ESA hasn't weighed in. It exists in that uncomfortable zone of reported but not proven, which means we have to hold it lightly. But we also can't ignore it, because if it's real, if there really was a 1.4 GHz transmission detected near Mars just as this object passed through, then we're not talking about a hypothesis anymore. We're talking about evidence. So here's where we are. An interstellar object entered our solar system on a hyperbolic trajectory, meaning it's not bound to the Sun and will eventually leave. It passed near Mars, possibly emitting radio signals. It swung around the Sun, brightening impossibly and changing colour. It appears to have accelerated and adjusted its course with precision, and now it's heading in Earth's general direction, arriving at closest approach in mid-December. Either we're witnessing the most extraordinary coincidence in cosmic history, or we're witnessing first contact. And over the next 14 parts, we're going to figure out which one it is. We're going to look at the data, examine the claims, explore the implications, and confront the possibility that has been lurking in the background of astronomy since humans first looked up at the stars and wondered, what if we're not alone? What if they're already here? What if this is how we find out? Part 2. Latest observational update. The data started pouring in long before anyone realized how strange this object would become. Sometimes the most extraordinary discoveries begin with routine observations, and 3I Atlas was no exception. On August 6th, 2025, the James Webb Space Telescope turned its near-infrared spectrograph toward the incoming visitor. JWST is not just any telescope. It's the most powerful infrared observatory ever built, capable of analysing the chemical composition of objects across vast distances with unprecedented precision. When JWST looks at something, we learn things we couldn't know any other way. We see molecules, temperature gradients, structural details invisible to other instruments. The JWST observations revealed something immediately odd about 3I Atlas. The spectral signature didn't match standard cometry profiles. There were unusual features in the near-infrared bands, hints of a composition that didn't quite fit the models. Scientists noted anomalies in the size estimates and physical properties that suggested this wasn't going to be a straightforward case. But at that point in early August, the object was still far from the Sun. It hadn't yet done anything truly impossible. So the data got filed, analysed, prepared for publication, just another interstellar visitor with some quirky chemistry. Then Hubble got involved. The Hubble Space Telescope, still going strong after decades in orbit, used its optical instruments to nail down the nucleus size. Their measurements suggested the solid core of 3I Atlas is likely less than 5.6 kilometers across. That's smaller than many city skylines. For comparison, Halley's comet has a nucleus about 15 kilometers long. 3I Atlas is a compact object, which makes its behavior even more puzzling. Smaller objects have less mass, which means any thrust or acceleration should be even more noticeable. There's less gravity to overcome, less inertia to fight. If this thing is accelerating, it shouldn't be subtle. Ground-based telescopes joined the party on August 27th, when Gemini South captured multicolour images showing the developing tail and evolving coma. A coma is the cloud of gas and dust that forms around a comet's nucleus as it heats up near the Sun. The Gemini images showed that 3i Atlas was indeed producing a coma, which was reassuring. See, it's behaving like a comet. It has a tail, it's outgassing, everything's normal. Except everything wasn't normal, and as the object approached perihelion, the weirdness intensified. Solar conjunction happened in late October, meaning 3i Atlas passed behind the Sun from Earth's perspective. During conjunction, ground-based telescopes can't observe an object because it's too close to the Sun's glare. We go temporarily blind. But spacecraft positioned in different orbits, particularly solar observation satellites, can still see. And that's when things got truly bizarre. SOHO, the Solar and Heliospheric Observatory, caught 3i Atlas in its field of view as the object swung around the Sun. GOES-19, a weather satellite, also picked it up. What they saw contradicted every expectation. Instead of fading as it rounded the Sun and began its outbound journey, the object brightened dramatically. The increase wasn't subtle. We're talking about a steep brightening curve that defied standard cometary physics. Objects don't get brighter after perihelion, unless something very unusual is happening. Then came the velocity measurements. Radar observations and positional tracking confirmed that 3i Atlas was moving at approximately 60 kilometers per second. That's roughly 130,000 miles per hour. For context, the fastest human-made object, the Parker Solar Probe, tops out around 430,000 miles per hour at its closest approach to the Sun, but that's after multiple gravitational assists and years of acceleration. 3i Atlas came into our solar system already moving at interstellar speeds, and it's maintaining that velocity with eerie consistency. The orbit itself tells a story. It's hyperbolic, which confirms interstellar origin beyond any doubt. Objects born in our solar system follow elliptical orbits bound to the Sun. Interstellar interlopers follow hyperbolic trajectories. They come in, swing around, and leave. But here's the kicker. 3i Atlas is on a retrograde orbit, meaning it's moving in the opposite direction of most solar system objects. It came in against traffic, threading through the planets backward. That's not impossible for a natural object, but it's less common. It's one more thing on the growing pile of oddities. Some researchers have suggested that 3i Atlas might be billions of years older than our solar system itself. The Sun is about 4.6 billion years old. Our planets formed from the same disk of material around the same time. But 3i Atlas may have formed around a star that died before our Sun even ignited. It could be a relic from a stellar system that no longer exists, wandering the galaxy for eons before stumbling into our neighbourhood. If true, this object is ancient beyond comprehension, carrying secrets from a time when our corner of the Milky Way looked completely different. Scientists have started calling 3i Atlas a black swan object. In statistics and risk analysis, a black swan event is something incredibly rare and unpredictable, something that falls so far outside normal expectations that it reshapes our understanding of what's possible. We've seen two previous interstellar objects, 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Oumuamua was weird, accelerating without visible outgassing. Borisov was normal, behaving like a standard comet. 3i Atlas is something else entirely. It's in a category by itself. All of this data, the JWST spectra, the Hubble size estimates, the Gemini imaging, the SOHO brightening observations, the velocity measurements, the orbital parameters, all of it sets the stage for what comes next. Because when you add up these observations, you start seeing patterns. You start noticing that this object isn't just unusual, it's behaving in ways that suggest intention, as if someone or something is controlling it. And when we look at the trajectory more closely, when we examine the acceleration data and the positional offsets, that suggestion becomes harder and harder to dismiss. Part 3. Trajectory and acceleration. Anomalies. Gravity is supposed to be simple. You have a mass, like the Sun. You have another mass, like a comet. The comet falls toward the Sun, swings around it, and flies back out into space following a precise mathematical curve. Kepler figured this out 400 years ago. Newton gave us the equations. Einstein refined them. We can predict planetary positions centuries in advance with perfect accuracy. Orbital mechanics is solved. It's textbook stuff. 3i Atlas did not read the textbook. The object follows a hyperbolic trajectory, which is exactly what we'd expect from an interstellar visitor. It came from outside the solar system, so it's not gravitationally bound to the Sun. It's just passing through, using our star's gravity to change direction before heading back out into the void. The perihelion distance, closest approach to the Sun, was calculated at approximately 1.4 astronomical units. That's inside the orbit of Mars, but well outside Earth's orbit. A safe distance, astronomically speaking. The object would never threaten Earth even if it wanted to. But here's where the math stops working. Near perihelion, observers reported a non-gravitational acceleration of approximately 0.02 millimeters per second squared. That number needs explanation. In space, acceleration is measured by how much an object's velocity changes over time. For a comet, we expect some acceleration from outgassing. As ice vaporizes, it creates jets of gas that push the comet around, slightly altering its path. This is normal, predictable, and thoroughly understood. The problem is magnitude and visibility. An acceleration of 0.02 millimeters per second squared is huge for a comet-sized object. To generate that kind of thrust naturally, you'd need massive, sustained outgassing. You'd need visible jets, a substantial dust tail, clear signs of material being ejected at high velocity. And while 3i Atlas does have a coma and some tail structure, observers note that the level of visible outgassing doesn't come close to matching the reported acceleration. It's like watching a car accelerate to highway speeds while the engine idles quietly. The effect doesn't match the apparent cause. Then there's the positional deviation. The Atacama Large Millimeter Array, ALMA, is one of the most precise astronomical instruments on the planet. It consists of 66 radio telescopes working together to create images with extraordinary resolution. When ALMA observes an object, it can pinpoint that object's location with incredible accuracy. And according to reports, ALMA found 3i Atlas approximately 4 arc-seconds away from where it should have been. 4 arc-seconds doesn't sound like much. It's a tiny angle, barely perceptible. But at interstellar distances, 4 arc-seconds translates to tens of millions of miles of spatial displacement. You don't drift that far by accident. Gravitational perturbations from planets might shift an orbit by fractions of an arc-second over time, but 4 arc-seconds represents a major deviation. Something pushed this object off its predicted path, and that something was powerful enough to be measurable across millions of miles. Now let's talk about photon pressure. Sunlight carries momentum. When photons from the sun hit an object, they exert a tiny force, like wind pushing on a sail. For objects with very low mass and high surface area, photon pressure can become significant. This is how solar sails work. A thin, reflective sheet can be accelerated to high speeds using nothing but sunlight. Could photon pressure explain 3i Atlas's acceleration? In theory, maybe. If the object had an extremely low density and a large surface area, sunlight might produce measurable thrust. But there's a problem. The acceleration is too strong, and it's happening in the wrong direction. Photon pressure should push objects away from the sun uniformly in all directions, like an expanding sphere of force. But 3i Atlas appears to be accelerating in a specific direction, with what looks like a course correction. That's not how photon pressure works. That's how rockets work. The timing is what makes this truly disturbing. The major acceleration and course deviation occurred near perihelion, at the closest point to the Sun. In spaceflight engineering, when you want to change your trajectory most efficiently, you do it at perihelion. That's where a small thrust produces the biggest change in orbit. It's called the Oberth effect. Any spacecraft designer knows this. And if 3i Atlas is executing a burn at perihelion, that suggests someone understands orbital mechanics. The alternative is that this is an astonishingly fortuitous accident. Maybe 3i Atlas has some bizarre internal structure that caused it to vent gas asymmetrically at exactly the right moment to produce a trajectory change that looks intentional, but is actually random. Maybe there's an undiscovered natural phenomenon that mimics intelligent guidance. Maybe we're seeing the universe's most elaborate coincidence. Or maybe something out there knows how to fly. Gravitational slingshots using a planet's gravity to change speed and direction are bread and butter for space agencies. Voyager did it. Cassini did it. Every mission to the outer solar system does it. You aim at a planet, let gravity pull you around, and emerge with a different velocity vector. It's free energy, free momentum, taken from the planet's orbital motion. And 3I Atlas's trajectory has the hallmarks of something that might be setting up for gravitational assists. It passed near Mars, it swung around the Sun, now it's heading toward Earth's orbital space. These aren't random flybys. They're positioned in space and time in ways that make you wonder if this object is navigating deliberately, using our planets as stepping stones, adjusting its course with precision while maintaining the cover story of a natural comet. If this is an engineered probe, it's playing the game brilliantly. It looks almost natural, almost explainable, but not quite. Just strange enough to make us notice, just controlled enough to make us wonder. And if the trajectory alone wasn't enough to raise eyebrows, the spectral data and composition analysis are about to make things even weirder. Part 4. Color, spectrum, and composition surprises. Every object in space has a signature, a unique fingerprint written in the light it reflects or emits. When we analyze that light, breaking it down into its component wavelengths, we can determine what something is made of, how hot it is, how fast it's moving. Spectroscopy is arguably the most powerful tool in astronomy. It lets us touch objects we can never physically reach. 3I Atlas's spectral signature is wrong, not slightly off, not a little unusual, wrong in ways that challenge our understanding of what interstellar objects should look like. Start with the nickel. At a distance of 3.88 astronomical units from the Sun, well beyond Mars's orbit, astronomers detected atomic nickel vapor in the coma of 3I Atlas. Nickel vapor, let that sink in. Nickel's melting point is about 1450 degrees Celsius. Its boiling point is nearly 3000 degrees. For nickel to vaporize and appear in a comet's coma, you need serious heat and some very specific chemistry, and yet there it was, glowing in the spectra, unmistakable. Now, nickel isn't unheard of in comets. Many comets contain trace amounts of metal, but the ratio is important. In typical comets, you see iron and nickel together, and the iron usually dominates. 3I Atlas reportedly shows an unusually high nickel-to-iron ratio, which is bizarre. Most solar system objects have fairly consistent metal ratios determined by the composition of the original solar nebula. When you see ratios that deviate significantly, it suggests the object formed somewhere else, under different conditions, possibly in a completely different stellar system with different metallicity. Some researchers have speculated that the high nickel content could indicate an artificial alloy. Nickel is used extensively in engineering because of its strength, corrosion resistance, and ability to withstand high temperatures. Stainless steel is an iron-nickel alloy. Superalloys used in jet engines and spacecraft contain significant nickel. If you were building a probe designed to survive interstellar space and close approaches to stars, you might choose a nickel-rich alloy for the hull. You might design it to ablate in specific ways, releasing metal vapor as a thermal control mechanism. But we're getting ahead of ourselves. Let's talk about color. As 3I Atlas approached perihelion, observers noted that it appeared bluer than the Sun. Objects in space generally don't get bluer as they approach a star. Dust reflects light in ways that make comets appear reddish or neutral. If anything, heating should drive off lighter volatiles and leave behind darker, redder material. But 3I Atlas went the other direction. It got bluer. Blue color suggests small particles scattering light, similar to why Earth's sky is blue. Rayleigh scattering occurs when light interacts with particles much smaller than its wavelength, but comets typically produce larger dust grains that scatter light differently. For 3I Atlas to appear blue, it would need to be producing either very fine dust or some other scattering mechanism entirely. Perhaps reflective metal particles, perhaps a structured surface with unusual optical properties. The brightness curve is equally strange. Observers noted that 3I Atlas's brightness increased with a steep dependence on distance from the Sun, following roughly an inverse power law with an exponent around -7.5. For comparison, typical comets follow a much gentler brightness curve. The steep dependence suggests either extremely volatile material vaporizing rapidly or a surface that becomes dramatically more reflective as it heats up. Neither explanation is particularly satisfying. Let's talk about the coma and tail. Comets are famous for their tails, vast streams of dust and gas stretching millions of miles behind them, pushed by solar wind and radiation pressure. The tail is what makes a comet spectacular. It's the visible proof of outgassing, the material escaping the nucleus as ice turns to vapor. 3i Atlas has a tail. Gemini South photographed it. But here's the issue. The tail is relatively modest compared to the reported acceleration. If the object is generating enough thrust to produce 0.02 mm per second squared of non-gravitational acceleration, we should see a substantial tail. We should see massive amounts of material streaming away, and while there is observable outgassing, it doesn't quite match the scale of thrust being reported. Furthermore, spectroscopic observations of the coma are missing some expected features. CN radicals, carbon-nitrogen compounds, are typically abundant in cometary comae. They're produced when organic molecules break down under solar radiation. CN is practically a hallmark of comets. But early observations of 3i Atlas's coma showed lower than expected CN levels. That's weird. It suggests either an unusual chemical composition or a different mechanism for producing the visible coma. Polarimetry adds another layer of strangeness. Polarimetry measures how light's electric field is oriented after reflecting off a surface. Different materials and structures produce different polarization signatures. Fluffy dust, smooth surfaces, metallic coatings, each produces a characteristic pattern. Observations of 3i Atlas using instruments like the SIMI telescope's Tri-CCS system revealed unusual polarization features. Specifically, there's evidence of a negative polarization branch that doesn't match standard cometary dust models. Negative polarization can indicate very small particles, smooth surfaces, or materials with specific optical properties. Some researchers have suggested this could point to a metallic or highly processed surface rather than the fluffy, porous structure typical of cometary nuclei. What does all this mean? If we try to build a natural explanation, we have to invoke a comet with unusual metal content, exotic chemistry, and surface properties unlike anything we've seen before. We have to assume it formed in a stellar system with radically different composition than ours, survived billions of years in interstellar space without significant alteration, and just happened to end up looking and behaving like something engineered. Or we can entertain the possibility that it is engineered, that the metallic composition is deliberate, that the unusual spectral features are byproducts of manufactured materials, that the modest tail is exactly what you'd expect from an object that's not actually outgassing much, but is instead using some other form of propulsion cleverly disguised as natural activity. Both explanations are extraordinary. One requires us to accept that nature can produce objects that perfectly mimic artificial ones through sheer coincidence. The other requires us to accept that we're not alone and that someone out there is visiting us. The question is which explanation is actually more likely. Part 5. Framing the hypothesis fork. We've reached the point where we need to step back and look at the whole picture, not just individual data points, not just isolated anomalies, but the complete pattern of behavior exhibited by 3i Atlas. Because when you line up everything we've discussed, the trajectory deviations, the unexplained acceleration, the unusual composition, the color changes, the spectral oddities, the timing, you're forced to confront a deeply uncomfortable question. Is this object natural or artificial? Let's be clear about what we mean by those terms. A natural object is something formed by astrophysical processes without intelligent intervention. A comet nucleus condensing from the disk around a young star. An asteroid shattered by a collision. A fragment of a destroyed planet wandering the galaxy. These objects obey physics passively. They don't make decisions. They don't adjust their trajectories. They don't emit radio signals. They simply exist, following the laws of nature like billiard balls on a cosmic table. An artificial object is something built, designed, engineered by an intelligence to serve a purpose. In our own solar system, we've sent 5 interstellar spacecraft, Pioneer 10 and 11, Voyager 1 and 2, and New Horizons. These are artificial objects that will eventually leave our solar system and wander the galaxy for millions or billions of years. If another civilization found one of them drifting through space, they would immediately recognize it as manufactured. It would look nothing like a natural object. So here's the fork in the road. Either 3i Atlas is natural, the most bizarre, statistically improbable, coincidence-packed interstellar object in the history of astronomy, or it's artificial, which means we are being visited by technology from another civilization. Let's walk through the natural explanation first. For 3i Atlas to be natural, we need to account for all its strange behaviors using only known physics and chemistry. The high nickel content could be explained by formation around a star with unusual metallicity. The acceleration could be explained by asymmetric outgassing we're somehow not detecting. The trajectory deviations could be gravitational perturbations we haven't properly modelled. The blue colour could be some exotic dust property. The timing of events could be pure coincidence. Each individual anomaly, taken alone, might have a natural explanation. But here's where Occam's razor becomes tricky. Occam's razor is the principle that the simplest explanation with the fewest assumptions is usually correct. But what counts as simple? Is it simpler to invoke half a dozen unlikely natural phenomena all occurring in the same object at the same time, or to invoke one artificial explanation that accounts for everything? The natural explanation requires us to accept a cascade of improbable events. That this object formed with unusual composition, survived interstellar space for billions of years, entered our solar system on a retrograde hyperbolic orbit, happened to pass near Mars at exactly the right time, accelerated near Perihelion through some undiscovered mechanism, changed colour in ways we don't understand, and is now heading toward Earth's orbital space. Each step is possible. All of them together strain credibility. Now let's look at the artificial explanation. If 3i Atlas is an engineered probe, everything makes sense. The metallic composition is structural material. The acceleration is propulsion, possibly a solar sail or some advanced drive system we don't understand. The trajectory adjustments are navigation. The colour change is thermal management or material properties of the hull. The timing isn't coincidence, it's planning. The object is following a mission profile, perhaps conducting observations, perhaps transmitting data home. The artificial explanation has the advantage of explanatory power. One hypothesis, intelligent design, accounts for all the anomalies. But it comes with a massive burden of proof. Because if we're wrong, if we claim artificial origin for a natural object, we've committed one of the greatest scientific blunders in history. We've shouted aliens when it was just a weird rock. But here's the thing that keeps me up at night. The cost of being wrong cuts both ways. If we dismiss an artificial object as natural because we're afraid of looking foolish, we miss first contact. We ignore the most important discovery in human history because it seems too extraordinary to believe. So how do we decide? Science gives us tools. We look for definitive signatures that can't be explained naturally, a radio transmission with information content, visible maneuvering thrusters, surface features that are obviously manufactured, deviations from ballistic trajectories that can't be attributed to any natural force. We search for the smoking gun, and that brings us to the most controversial claim surrounding 3i Atlas. The claim that 3 weeks before perihelion, as the object passed near Mars, it emitted radio signals at 1.4 GHz. The hydrogen line, the universal calling card, the frequency that any technological civilization would know is special. If that claim is true, and I cannot stress enough that it remains unverified, then we're not in hypothesis territory anymore. We're in evidence territory. A radio transmission at a meaningful frequency, timed with the object's approach, would be the smoking gun. It would shift the conversation from could this be artificial to how do we respond? But even without the radio claim, the accumulated weight of anomalies is pushing the needle. Every additional observation that doesn't fit the natural model makes the artificial hypothesis more plausible. We're watching a Bayesian probability calculation play out in real time. Prior probability of artificial interstellar visitors is low. We've never confirmed one before. But the likelihood of the data given natural explanations is also low. And when natural explanations become sufficiently unlikely, even improbable hypotheses gain traction. Here's what I think we're really dealing with. We're witnessing a test. Not a test imposed by the object. We have no evidence it cares what we think. A test of our own cognitive flexibility. Can we hold multiple contradictory ideas simultaneously? Can we investigate the artificial hypothesis seriously without jumping to conclusions? Can we maintain scientific rigor while exploring what might be the most important question we've ever asked? The data isn't finished. 3i Atlas is still observable. It's still moving, still potentially doing strange things. As we dig deeper into the hidden angles, the material clues, the paradoxes of outgassing and thrust, we'll build a more complete picture. We'll see if the natural explanation holds up or collapses under the weight of accumulating evidence. Because make no mistake, we are on the edge of something profound. Either we're about to witness nature doing something we never imagined possible, or we're about to confirm that we are not alone in the universe. Either way, the answer is extraordinary. And the clock is ticking toward December 19th, when 3i Atlas makes its closest approach to Earth. Part 6. Material and Structure Clues. Physics gives us tools to peer inside objects we can never touch. One of the most powerful is polarimetry, the study of how light's orientation changes when it bounces off a surface. When unpolarized sunlight hits an object and reflects back toward us, the way that light becomes polarized tells us about the surface structure, the particle sizes in any surrounding dust, and even the chemical composition of materials. 3i Atlas's polarization signature is giving scientists headaches. Standard cometary dust produces a well-understood polarization pattern. Light reflecting off fluffy, porous material, the kind of stuff that makes up typical comet nuclei, creates positive polarization at certain scattering angles, and negative polarization at others. The specific pattern reveals grain sizes, composition, and structure. Astronomers have studied dozens of comets this way. We know what normal looks like. 3i Atlas is not normal. Observations using instruments like the SEMI telescope's Tri-CCS spectropolarimetry system revealed an unusual negative polarization branch. The light coming off this object is polarized in ways that don't match standard cometary dust models. This could mean several things. Maybe the particles in the coma are much smaller than typical cometary dust, causing different scattering behavior. Maybe the surface of the nucleus itself has unusual properties, highly reflective, smooth, or structured in ways that produce anomalous polarization. Or maybe we're looking at materials that don't naturally occur in comets. Metallic surfaces, for instance, can produce distinctive polarization signatures. So can manufactured structures with ordered features at scales, comparable to the wavelength of visible light. If 3i Atlas has a metallic hull or surface features that are too regular, too organized, that would show up in polarimetry data as something off. The challenge with polarimetry is interpretation. The data tells us something is unusual, but it doesn't hand us a simple answer. We have to build models, test hypotheses, and see which ones fit. And right now, the models that fit best are either exotic natural materials we've never seen before or artificial materials doing exactly what artificial materials would do. Let's talk about composition more directly. The detection of nickel vapor at large distances from the Sun is a red flag. Nickel has a high vaporization temperature. For it to appear in significant quantities in the coma at 3.88 astronomical units, the nucleus must contain a lot of nickel, and something must be liberating it into space despite the relatively low solar heating at that distance. Natural comets contain metals, but they're typically locked up in silicate grains or refractory minerals that don't vaporize easily. You need high temperatures to free metal atoms, yet 3i Atlas is releasing nickel vapor while still far from perihelion. This suggests either an unusual internal heat source, perhaps from radioactive decay of short-lived isotopes, or a surface that's actively ablating, shedding material through some mechanism other than simple solar heating. Ablation is exactly what spacecraft heat shields do. When a capsule re-enters Earth's atmosphere, friction generates enormous heat. The heat shield ablates, carrying away thermal energy and protecting the spacecraft. If 3i Atlas has a metallic coating or hull designed to survive close stellar passes, we might expect it to ablate controlled amounts of material, releasing metal vapor as a thermal management system. The nickel we're seeing could be deliberate, not incidental. Then there's the question of density and structure. Cometary nuclei are typically porous, with densities well below that of solid ice. They're fluffy, like cosmic snowballs mixed with dust. But if 3i Atlas is producing strong acceleration with relatively modest visible outgassing, it might be denser than a typical comet. A denser object would have more mass per unit volume, which would make the observed acceleration even harder to explain naturally. You'd need even more thrust to push it around. But a denser object is exactly what you'd expect from an engineered probe. Spacecraft are not fluffy. They're packed with equipment, structural components, shielding, propulsion systems. An artificial probe disguised as a comet might deliberately include volatile materials on its surface to create a convincing coma, while the bulk of its mass remains locked up in dense, manufactured structures beneath. Imagine building an interstellar probe and wanting it to pass through stellar systems unnoticed, or at least unremarkable. You'd coat it in ice and dust. You'd design it to outgas naturally when heated, producing a cometary appearance. But underneath you'd have metal, ceramics, electronic components, possibly even exotic materials we don't have names for. From a distance, it looks like a comet. Up close, Under the right analysis, the facade starts to crack. We have to consider the possibility of radiation shielding. Interstellar space is not empty. It's filled with cosmic rays, high-energy particles that bombard anything travelling through it. Over millions or billions of years, cosmic rays degrade materials, alter chemistry, and destroy organic molecules. Any probe travelling between stars would need serious radiation shielding to survive the journey. Nickel happens to be excellent for radiation shielding. It's dense, relatively abundant, and blocks high-energy particles effectively. A hull made from nickel-rich alloys would protect delicate instruments and maintain structural integrity across vast timescales. The fact that we're seeing nickel vapor could indicate that the outer layers of such a shield are ablating away as the object heats up, revealing its true composition. There's also the question of age. Some analyses suggest 3I Atlas could be billions of years older than our solar system. Our Sun formed 4.6 billion years ago. If this object predates that, it formed around a different star, possibly one that has already died. That means it's been wandering the galaxy for an incomprehensible span of time, possibly passing through multiple stellar systems, possibly collecting data from each one. The natural explanation for such extreme age is straightforward. Some objects really are that old. The galaxy is full of ancient debris. But if we're entertaining the artificial hypothesis, the age becomes even more staggering. A probe billions of years old would represent a civilization so advanced, so long-lasting, and so committed to exploration that they built machines designed to function across cosmological timescales. That's a level of technological sophistication that makes our own achievements look like cave paintings. Consider what happens to materials over billions of years in space. Micrometeorite impacts pit and erode surfaces. Cosmic rays alter the crystalline structure of metals and minerals. Ice sublimates slowly even in the cold of interstellar space. Any natural object should show signs of this weathering. But an artificial object might be designed to weather in specific ways, to maintain function despite damage, perhaps even to self-repair using mechanisms we can barely imagine. The surface structure of 3I Atlas remains largely unknown. We don't have high-resolution images of the nucleus. We can't see whether it's rough or smooth, cratered or pristine, random or ordered. But the polarimetry hints at something unusual. The spectral signatures suggest composition that doesn't fit standard models. The behavior indicates either physics we don't understand or engineering we're reluctant to acknowledge. And then there's the outgassing paradox, because while we're seeing evidence of a coma and tail, the amount of material being ejected doesn't match the amount of acceleration being produced. The math doesn't work. The thrust is too strong for the visible outgassing. Something else is happening, something we're either not detecting or not understanding, which brings us directly to the central mystery of 3I Atlas. How is this thing accelerating? Part 7. Outgassing and Thrust Paradox. Comets are rockets. That's not a metaphor, it's physics. When a comet approaches the Sun, solar heating causes ices beneath the surface to vaporize. The expanding gas bursts through the crust, carrying dust particles with it. This ejection creates thrust, pushing the comet in the opposite direction of the gas jet. It's Newton's third law. Every action has an equal and opposite reaction. The comet shoots out material and the comet itself recoils. This process is called non-gravitational acceleration, and it's completely normal. Astronomers account for it when calculating orbits. We measure it, model it, and predict how it will affect trajectories. For most comets, the acceleration is small, consistent, and directly correlated with the amount of visible outgassing. More gas, more dust, more thrust. It's a simple, elegant relationship. 3I Atlas is breaking that relationship. The reported acceleration, approximately 0.02 millimeters per second squared, is substantial. To put that in perspective, it's about 200 times stronger than the acceleration typically seen from cometary outgassing on objects of similar size. If you were standing on the surface of this object, you wouldn't feel it. It's far too weak for human perception. But over days and weeks, as the object moves millions of miles, that continuous acceleration adds up. It shifts the trajectory measurably, moving the object off its predicted path by millions of miles. To generate that much thrust through outgassing, you need to eject a lot of material at high velocity. Gas expanding from a heated surface doesn't move particularly fast, maybe a few hundred meters per second at most. To produce significant thrust, You need either enormous quantities of gas or some mechanism to accelerate that gas to much higher speeds. Here's the problem. When telescopes observe 3I Atlas, they see a coma and a modest tail. There's definitely outgassing happening, but the amount of visible material being ejected doesn't match what would be required to produce the reported acceleration. It's not even close. The observations suggest relatively modest activity, while the trajectory measurements demand vigorous, sustained mass ejection. This is the outgassing paradox. The thrust exists, we can measure it in the changing trajectory, but the source of that thrust is invisible or undetected. Let's consider possible explanations. Maybe the outgassing is happening in ways we're not seeing. Perhaps the jets are directed away from Earth, so we're viewing them edge on and missing most of the activity. Perhaps the ejected material is composed of gas molecules that don't show up well in visible light, making the activity less apparent than it actually is. These are plausible scenarios that would help reconcile the observations with the measurements, but there's a limit to how much we can hide. JWST observed this object in infrared. Hubble observed it in optical wavelengths. Ground-based telescopes captured it in multiple color bands. Spacecraft observed it from different angles during solar conjunction. We're not looking at this thing from just one perspective. We're surrounding it with instruments, and collectively they're not seeing enough outgassing to explain the thrust. Another possibility involves the composition of the ejector. Maybe 3I Atlas is ejecting primarily metal vapor, rather than the usual water and dust. Metal vapor jets could produce thrust with less visible signature than dusty outgassing. Nickel vapor, which we know is present, doesn't scatter light the same way silicate dust does. A stream of metal atoms might be nearly invisible except in specific spectroscopic observations. This brings us to an interesting question. Why would a comet eject primarily metal vapor? Natural comets don't do that. They eject water, carbon dioxide, carbon monoxide, and various organic compounds, along with silicate dust. Metals are present but not dominant. For 3I Atlas to be ejecting significant metal vapor, it would need a very unusual composition, an iron-nickel core perhaps, with only a thin layer of volatiles on top. That description sounds an awful lot like a spacecraft hull with a coating of camouflage ice. Now let's talk about solar sails. A solar sail is a large reflective surface that uses photon pressure from sunlight to generate thrust. Photons have momentum, and when they reflect off a surface, they transfer that momentum to the object. The thrust is incredibly weak, far weaker than chemical rockets, but in space, where there's no friction and no air resistance, even weak continuous thrust adds up over time. Could 3I Atlas be using a solar sail? The math gets tricky. To generate 0.02 millimeters per second squared of acceleration from photon pressure alone, you'd need a very large surface area relative to the object's mass. For a 5-kilometer nucleus, you'd need either extremely low density or a sail structure much larger than the nucleus itself. We don't see a large sail structure. We see what looks like a small nucleus with a modest coma. But what if the sail isn't a traditional flat sheet? What if it's a multi-layer structure wrapped around the nucleus, or a coating with unusual reflective properties, or some configuration we haven't imagined because we're thinking in terms of our own? Primitive sail designs? Advanced civilizations wouldn't build solar sails the way we do. They'd have materials we can't make, structures we can't conceive, and optimization we can't match. A probe from such a civilization might use photon pressure in ways that produce thrust without looking like a sail at all. The blue color shift could be relevant here. A highly reflective surface tuned to specific wavelengths might appear blue, while efficiently converting solar radiation into thrust. There's also the timing to consider. The major acceleration and course deviation occurred near perihelion, when the object was closest to the Sun and experiencing maximum solar radiation. That's exactly when a solar sail would be most effective. It's also exactly when a spacecraft using solar power for any propulsion system would have maximum energy available. In orbital mechanics, there's a principle called the Oberth effect. When you're moving fast and deep in a gravity well, a small thrust produces a larger change in orbital energy than the same thrust applied elsewhere. Spacecraft designers use this deliberately. They fire engines at perihelion to get the most bang for their buck. If 3I Atlas executed a propulsive maneuver at perihelion, that shows sophisticated understanding of orbital mechanics. Or, if we're clinging to the natural explanation, it shows that nature happened to create a situation where outgassing peaked at precisely the moment when it would most efficiently alter the trajectory. Possible, but increasingly strained. The brightening behaviour adds another layer of strangeness. After perihelion, as 3i Atlas moved away from the Sun, it got brighter instead of dimmer. Natural comets don't do this. Brightness should correlate with distance from the Sun. Closer means more solar heating, more outgassing, brighter coma. Farther means less heating, less activity, dimmer appearance. But spacecraft do get brighter after perihelion if they're deploying solar panels, extending antennas, changing orientation, or activating systems that were dormant during closest approach. A probe that just executed a close solar pass might need to reconfigure itself, extend heat radiators, or adjust its structure in ways that change its reflectivity. The observations from SOHO and GOES 19 are particularly interesting because they caught this brightening in real time. These spacecraft aren't designed for asteroid observation, they monitor the Sun. But 3i Atlas passed through their fields of view, and they documented something that shouldn't happen. An object getting brighter as it leaves the Sun, defying every expectation of cometary physics. Every time we try to explain 3i Atlas using natural mechanisms, we have to invoke special circumstances, unusual compositions, and fortuitous timing. Every time we consider the artificial hypothesis, the behaviour makes sense immediately. The thrust paradox isn't a paradox if the thrust comes from technology. The brightening isn't mysterious if it's a system activation. The course correction isn't luck if it's navigation. But proof requires more than suspicious coincidences. It requires direct evidence. And that's where the radio claims become absolutely critical. Because if 3i Atlas is transmitting, if it's sent out a signal that we detected, then we're not speculating anymore. We're listening to first contact. Part 8. Radio ping claim and SETI context. There's a frequency that every radio astronomer knows by heart. 1.4204057.5 GHz, 21 centimeters, the hydrogen line. Hydrogen is the most abundant element in the universe. When hydrogen atoms flip their electron spin state, they emit radiation at exactly this frequency. It's universal, unchanging, and utterly fundamental. In 1959, physicists Giuseppe Cocconi and Philip Morrison published a paper suggesting that any civilization wanting to send interstellar messages would use this frequency, because any civilization capable of radio astronomy would be monitoring it. It's the most obvious channel for communication, written into the structure of matter itself. SETI, the search for extraterrestrial intelligence, has been listening at 1.4 GHz for decades. The famous WOW signal detected in 1977 occurred at 1.420 MHz right in the hydrogen line. That signal remains unexplained. It appeared once, for 72 seconds, and never repeated. It was so unusual, so powerful, and so precisely tuned that the astronomer who discovered it wrote WOW on the printout, hence the name. Now, on October 3rd, 2025, roughly 3 weeks before 3i Atlas reached perihelion, reports emerged of radio emissions detected near Mars at 1.4 GHz, the same frequency, the universal calling card. I need to be absolutely clear about the status of this claim. It is unverified. No major observatory has publicly confirmed it. NASA has not released a statement. The European Space Agency has not weighed in. The claim exists primarily in amateur astronomy circles, social media posts, and speculative discussions. It has not appeared in peer-reviewed literature. We do not have published instrument data confirming the detection. That said, we also can't simply ignore it. Because if the claim is true, if there really was a coherent radio emission at 1.4 GHz, originating from the vicinity of 3i Atlas as it crossed near Mars, then everything changes. That would be direct evidence of artificial origin. Natural objects don't emit narrow-band radio signals at meaningful frequencies. They produce broad-spectrum noise, thermal radiation, or emissions tied to physical processes like lightning or magnetic field interactions. A signal at precisely the hydrogen line isn't ambiguous. Let's examine the timing. October 3rd was when 3i Atlas crossed the ecliptic plane near Mars's orbital distance. This wasn't particularly close to Mars itself. Space is vast, and near Mars in astronomical terms can mean millions of miles away. But it was a significant moment in the object's trajectory, a crossing point, a milestone. Then came October 29th, perihelion. That's 26 days after the claimed radio event. Then December 19th, closest Earth approach. That's 51 days after perihelion. The intervals are oddly precise, 26 days, then 51 days. Neither interval is a round number, but they're not random either. They suggest scheduled events, waypoints on a planned trajectory. If you're a civilization sending a probe through a star system, you'd want it to transmit periodically. Update home with status reports, beacon its position to other assets in the system, signal its findings. A transmission near Mars makes sense. It's far enough from the Sun that solar radio noise is reduced, making the signal cleaner. It's also geometrically positioned where Earth-based receivers might detect it if they're listening at the right time. The problem is verification. Radio astronomy is hard. The sky's full of radio noise, from Earth-based transmitters, from satellites, from natural cosmic sources. Detecting a genuine extraterrestrial signal requires careful analysis to rule out interference. You need multiple observations, ideally from different locations with consistent characteristics that can't be explained as terrestrial contamination. The claimed 1.4 GHz ping doesn't yet meet those criteria. We don't have published data from multiple observatories. We don't have detailed analysis of the signal characteristics. We don't have follow-up observations confirming repetition or structure. What we have are reports, which in science means very little until they're substantiated. But here's what makes this particularly frustrating. If the signal was real but brief, a short burst, perhaps just seconds or minutes long, it might have been missed by most instruments. Radio telescopes don't monitor the entire sky continuously. They point at specific targets, observe for scheduled durations, then move on. A transient signal can easily slip through the gaps, detected by one instrument but missed by others, leaving us with unconfirmed claims and ambiguity. SETI protocols exist for this exact scenario. When a candidate signal is detected, you immediately attempt to reacquire it. You point other telescopes at the source. You schedule follow-up observations. You check for repetition. The WOW signal failed these tests. It never appeared again, which is why it remains a mystery rather than confirmed contact. For 3i Atlas's claimed signal to be verified, we'd need it to repeat or have been recorded with sufficient detail that analysis can confirm its artificial origin. As of now, that hasn't happened publicly, which leaves us in an uncomfortable limbo. The claim exists. It fits the artificial hypothesis perfectly, but it's unproven, which means we can't rely on it as evidence. Let's place this in broader SETI context. When 1I/Oumuamua, the first confirmed interstellar object, passed through. In 2017, SETI researchers at the Breakthrough Listen project pointed radio telescopes at it. They listened for any sign of transmission. They found nothing. Oumuamua remained silent, or if it spoke at frequencies or in ways we weren't monitoring. 3i Atlas is different. It's brighter, more active, and exhibiting more anomalous behavior. If SETI groups are monitoring it, and they almost certainly are, they're using the most sensitive instruments available. The Greenbank telescope, the Parkes telescope, possibly even the Very Large Array. If 3i Atlas is transmitting, we have a decent chance of detecting it. The silence so far is not necessarily meaningful. Absence of evidence isn't evidence of absence, especially in radio astronomy where coverage is sparse and signals can be faint or intermittent. But if we reach December 19th, and no confirmed transmissions have been detected, that would weaken the artificial hypothesis considerably. On the other hand, if a transmission is confirmed, if we get clear, repeated, narrow-band emissions at meaningful frequencies with structure that can't be explained naturally, then we're in uncharted territory. First contact wouldn't be landing on the White House lawn. It would be this, a distant object, moving through our solar system, speaking in the language of physics and announcing its presence to anyone capable of listening. The implications are staggering. A confirmed artificial signal means we're not alone. It means interstellar travel is possible. It means there's intelligence out there advanced enough to build probes that cross between stars. It means they know we're here, or at least they're surveying systems like ours. And it means that for the first time in human history we have evidence of technology not built by human hands. But we're not there yet. The radio claim remains unverified. The silence from major institutions is deafening. And in the absence of confirmation, we have to treat it as speculation, tantalizing, consistent with the artificial hypothesis, but not proof. What we can say with certainty is that 3i Atlas's trajectory is suspicious. The timing of events is suspicious. The alignment with key points in our solar system is suspicious. And if you're building a probe designed to navigate through a star system, using gravitational assists and planned encounters with planets, then what we're seeing is exactly what we should expect. Which brings us to the question of trajectory alignment, gravitational assists, and whether this object is flying or falling. Part 9. Gravitational assist and trajectory alignment. Space is big, incomprehensibly, almost impossibly big. The odds of an interstellar object randomly entering our solar system and passing near multiple planets are vanishingly small. The odds of it doing so while executing course corrections at optimal moments are effectively zero, unless it's not random. Gravitational assists, also called gravity assists or slingshots, are fundamental to interplanetary travel. The principle is simple. You approach a planet, fall toward it, swing around it, and emerge with your velocity changed. You've stolen momentum from the planet's orbital motion, gaining speed without burning fuel. Voyager 1 used gravitational assists at Jupiter and Saturn to reach the outer solar system and eventually escape the Sun's gravity entirely. Every mission to the outer planets uses this technique. It's free energy, harvested from orbital mechanics. But it requires precision. You have to approach the planet at exactly the right angle, at exactly the right time. A few degrees off and you miss the optimal trajectory. A few hours early or late and the planet isn't where you need it to be. Gravitational assists are not accidents. They're carefully planned maneuvers requiring detailed knowledge of orbital mechanics. 3I Atlas's trajectory hits waypoints with disturbing precision. October 3rd, the object crossed near Mars. Not a collision. Mars is a tiny target in the vastness of space, but a passage through the same general region, close enough that Mars's gravity could potentially influence the trajectory. This is when the claimed 1.4 GHz radio ping occurred. Whether or not that claim is real, the Mars encounter itself is documented. The object passed through. Then, October 29th, Perihelion. Closest approach to the Sun at approximately 1.4 astronomical units. This is where the major acceleration and course deviation occurred. This is where the brightening happened. This is the critical moment in the trajectory. Then December 19th, closest approach to Earth's orbital space. 3I Atlas won't pass particularly close to Earth itself, still millions of kilometers away, but it will be at its nearest point, positioned where Earth-based observations are optimal. The intervals between these events are 26 days from Mars to perihelion, then 51 days from perihelion to Earth approach. Some analysts have noted that these numbers, when broken down, seem to echo orbital resonances and mathematical relationships common in celestial mechanics. Whether that's meaningful or coincidence remains debatable, but it adds to the growing pile of things that feel too precise to be random. Now here's where it gets genuinely eerie. The trajectory of 3I Atlas, when projected backward into space and forward toward its departure, appears to align within roughly 9 degrees of the region where the WOW signal originated in 1977. The WOW signal came from the direction of Sagittarius, somewhere near the star group around Chi Sagittarii. It was a strong narrow-band radio signal at 1.420 MHz that lasted 72 seconds and never repeated. For nearly 50 years, it's remained one of the most compelling candidate SETI detections, unexplained and tantalizing. If 3I Atlas's trajectory genuinely points back toward the same region, that's either the most extraordinary coincidence imaginable or it's related. A probe originating from that region would naturally approach from that direction. It would enter our solar system with a velocity vector pointing back toward home. I need to stress that this alignment claim is speculative and depends on trajectory calculations that carry uncertainties. Small errors in measuring velocity and position can create large errors when extrapolating across interstellar distances. We're not talking about a precise alignment. 9 degrees is actually a fairly wide cone in astronomical terms. But it's close enough to raise eyebrows. Let's talk about what natural interstellar objects should do. They should follow hyperbolic trajectories determined entirely by their incoming velocity and the Sun's gravity. Once you know an object's position and velocity at any point, you can calculate its entire path with high precision. Gravitational perturbations from planets will cause small deviations, but these are predictable and minor. Natural objects don't make course corrections. They don't accelerate at perihelion. They don't arrive with trajectories conveniently aligned with planetary encounters. 3I Atlas does all of those things. The European Space Agency's Mars orbiters, Mars Express and the Trace Gas Orbiter, attempted to observe 3I Atlas during its near-Mars passage. They had a unique vantage point, positioned where they might catch the object in their cameras. But the observations were challenging. The object was moving fast, appeared faint, and required precise pointing and long exposures. Initial imaging attempts didn't detect it clearly, though that doesn't mean it wasn't there, it just means the observations were at the edge of what the instruments could manage. The absence of clear Mars orbiter images is frustrating but not surprising. These spacecraft weren't designed for asteroid hunting. Their cameras are optimized for surface imaging, not deep space objects. Catching a fast-moving interstellar visitor required observation windows measured in minutes, with exposures long enough to collect sufficient light but short enough to avoid motion blur. It's technically difficult, and the conditions weren't ideal. But here's the thing. If 3I Atlas really is an artificial probe, it might have deliberately timed its Mars passage to avoid close scrutiny. Or it might have been actively transmitting or observing Mars, treating the encounter as an opportunity to gather data on another planet in the system. We can't know without better observations or confirmed signals. The trajectory analysis shows that 3I Atlas will eventually leave our solar system on an outbound hyperbolic path, heading back into interstellar space. If it's natural, it will drift silently for millions of years until perhaps encountering another star system by chance. If it's artificial, it's completing a mission, surveying our solar system, gathering data, perhaps transmitting findings home, then departing to continue its journey or to report what it's learned. The mathematics of the trajectory are elegant. Too elegant, some would say. Everything lines up just a little too well. The planetary encounters, the timing, the perihelion distance optimized for solar energy collection, the outbound path that ensures visibility from Earth during December. If you were planning a survey mission through an inhabited star system, this is exactly how you'd design the flyby. Maximum data collection, minimal risk, precise timing to observe multiple worlds. Or it's all coincidence, an interstellar rock that just happened to enter at the right angle, just happened to pass near Mars, just happened to accelerate at perihelion through some natural process, just happened to be heading toward Earth's orbital neighborhood at the optimal observation time. Possible, but requiring an extraordinary sequence of fortunate accidents. The Bayesian calculation keeps shifting. Each new piece of data that doesn't fit natural explanations pushes the probability needle toward artificial. But we're still not at certainty. We're at discomfort, at suspicion, at this needs serious investigation, rather than this is definitely aliens. Which brings us to the institutional response. How are major space agencies and observatories reacting to 3I Atlas? What are they saying publicly? What might they be saying privately? And why does the flow of information feel controlled? Part 10. Controversies and Institutional Dynamics. Science is supposed to be transparent. Data gets published, findings get peer-reviewed, discoveries get announced. When something extraordinary is observed, the scientific community discusses it openly, debates interpretations, and collaborates to figure out what's really happening. That's the ideal. 3I Atlas isn't following that script. The media coverage has been schizophrenic. Mainstream science news outlets describe it as an unusual interstellar comet with some interesting properties. The language is careful, measured, emphasizing that while the object shows unexpected behaviors, natural explanations remain plausible. NASA's public statements have been sparse, mostly confirming basic observational facts without speculation. Then you have tabloid coverage. The New York Post ran articles highlighting the unusual nickel composition, calling it a refined nickel alloy, and openly discussing artificial origin hypotheses. Other outlets have picked up on the acceleration anomaly, the trajectory oddities, and the radio ping claims, framing the story as potential alien visitation. The gap between these narratives is stark. Either 3I Atlas is a mildly interesting comet that happens to be a bit weird, or it's the most important astronomical discovery in history. There's no middle ground being discussed. It's binary. Natural and boring versus artificial and civilization-altering. Part of this reflects legitimate scientific caution. Scientists are trained to avoid extraordinary claims without extraordinary evidence. The stakes are enormous. If a researcher publicly suggests alien origin and turns out to be wrong, their career suffers. They become known as the person who cried alien. The incentive structure of academia punishes speculation, rewards caution, and filters out bold claims unless they're ironclad, but caution can become suppression. There are whispers, unconfirmed but persistent, that data access has been tightened, that certain observations are being held back from public release, pending further analysis. That coordination between observatories is happening through non-public channels. This might be standard procedure for managing sensitive findings, or it might be institutional gatekeeping, controlling the narrative until officials decide what to tell the public. The Mars HiRISE imaging controversy is illustrative. HiRISE is a high-resolution camera on NASA's Mars Reconnaissance Orbiter, capable of imaging surface features down to meter-scale resolution. In theory, it could have been pointed at 3I Atlas during the Mars encounter to capture detailed images. According to some reports, imaging was attempted, but the results were delayed or not released due to a government shutdown affecting data processing and publication timelines. This explanation is plausible. Government shutdowns do disrupt operations. Data processing does take time, but the timing feels suspicious. A potential alien probe passes near Mars, imaging is attempted, and then bureaucratic complications prevent public release. It's the kind of scenario that breeds conspiracy theories, even if the reality is mundane. Individual scientists have been more forthcoming. Avi Loeb, the Harvard astrophysicist who championed the artificial origin hypothesis for Oumuamua, has published analyses of 3I Atlas highlighting the acceleration anomaly. His calculations suggest the observed thrust exceeds what natural outgassing should produce, supporting the idea that something else is happening. Loeb has been willing to publicly entertain the artificial hypothesis, arguing that we should investigate thoroughly rather than dismissing it out of hand. Other scientists have pushed back. Michael Kuppers from the European Space Agency, speaking to journalists, stated that 3I Atlas looks like a comet despite its oddities. The implication is that while unusual, the object still fits within the range of natural phenomena. This is the conservative position. Acknowledge the weirdness, but maintain that natural explanations remain viable until definitively ruled out. The tension between these positions reflects deeper divides in the scientific community. How much evidence is required before we seriously consider artificial origin? What counts as definitive proof? And who decides when the threshold has been met? There's also the ethical dimension. If 3I Atlas is artificial, who should control the information? Government space agencies, the scientific community, the public. Different entities have different interests. Governments might want to assess potential threats or opportunities before disclosure. Scientists want to ensure accuracy before making announcements. The public arguably has a right to know immediately if we're being visited. These competing interests create friction. Data gets withheld for analysis. Announcements get delayed pending confirmation. Speculation fills the vacuum, and in the absence of official information, rumours and unverified claims proliferate. The 1.4 GHz radio ping exists in this space, reported by some, unconfirmed by authorities, impossible to verify without institutional data release. There's also the question of what happens if artificial origin is confirmed. International protocols exist for handling potential contact, developed by SETI researchers and international bodies. The guidelines emphasize careful verification, coordinated announcement, and transparency. But these are recommendations, not laws. There's no enforcement mechanism. If a space agency confirms artificial origin, they're not legally obligated to inform the public immediately. That's unsettling. We could be in a situation where those with access to data know more than they're saying, where institutional dynamics are shaping what information reaches public awareness. Whether that's happening with 3I Atlas is unknown. But the pattern of limited disclosure, cautious statements, and delayed data release is consistent with sensitive information being managed carefully. The broader context matters here. We're living through a period of renewed interest in unidentified aerial phenomena. Governments are acknowledging that unidentified objects have been observed in restricted airspace performing maneuvers that challenge conventional explanations. While those phenomena are separate from 3I Atlas, they've shifted the conversation. It's become marginally more acceptable to discuss non-human technology without immediate dismissal. 3I Atlas arrives in this environment, an interstellar object behaving strangely, observed by multiple instruments, generating data that doesn't quite fit natural models. The institutional response is cautious, the public discourse is divided, and the data remains incomplete. We're left reading between the lines, interpreting silences and wondering what we're not being told. As December 19th approaches, closest Earth, approach, the observation window intensifies. More telescopes will be trained on the object, more data will be collected, perhaps definitive measurements will emerge that resolve the ambiguity. Or perhaps we'll get more of the same, intriguing anomalies, incomplete explanations, and institutional caution that leaves the question unanswered. But to fully understand what 3i Atlas means, we need to zoom out. We need to place this object in the context of interstellar visitors generally, and consider what its behaviour, whether natural or artificial, tells us about the universe we inhabit. Part 11. Interstellar Objects and what 3i Atlas means. Before 2017, we had never confirmed an interstellar object passing through our solar system. Theoretically, we knew they should exist. Models predicted that rocky and icy debris gets ejected from forming planetary systems, scattered by gravitational interactions, and ends up wandering the galaxy. But seeing one requires luck. They're faint, fast-moving, and easily missed. Then came Oumuamua, 1i/Oumuamua, discovered in October 2017 by the Pan-STARRS telescope in Hawaii. The name means scout, or messenger, in Hawaiian, and it was fitting. Oumuamua was unlike anything we'd seen. It entered our solar system on a hyperbolic trajectory, passed close to the Sun, and was already outbound when discovered. Its shape appeared elongated, possibly cigar-like, and it exhibited non-gravitational acceleration without visible outgassing. Oumuamua launched 1,000 debates. Natural comet with unusual properties, fragment of a shattered planet, nitrogen iceberg from a Pluto-like world, or, as Avi Loeb suggested, an artificial light sail or probe. The data was insufficient to decide definitively, and Oumuamua escaped before we could study it thoroughly. It's now too far and too faint to observe, leaving us with questions instead of answers. 2 years later, 2019, we detected 2i/Borisov. This one was different. It behaved like a standard comet, outgassing visibly, showing a normal composition, following predictable physics. Borisov was reassuring. See, interstellar comets can be normal. Not every visitor is bizarre. Now we have 3i Atlas, and we're back to bizarre. If Oumuamua opened the door to questioning whether interstellar visitors might be artificial, 3i Atlas is kicking that door wide open. Bigger, brighter, more active, and exhibiting behaviours that challenge natural explanations even more strongly than Oumuamua did. So what does this pattern tell us? We have 3 confirmed interstellar objects. One weird, one normal, one extremely weird. That's a tiny sample size, statistically meaningless. But it suggests that interstellar space might be more crowded than we thought, and that the objects passing through are diverse. Some are mundane, others are anything but. Interstellar objects offer a unique opportunity. They're samples from other stellar systems delivered to our doorstep for free. We don't have to travel light years to study them, we just have to notice them passing by and point our instruments quickly. Every interstellar visitor carries information about its home system, composition that reflects the chemistry of its parent star, structure shaped by formation conditions, and potentially, in the case of artificial objects, technology that reveals the capabilities of other civilizations. 3i Atlas is forcing us to revise models of what interstellar objects can be. If it's natural, then nature produces objects far stranger than our models predicted. We need to account for high metal content, exotic outgassing mechanisms, and structural properties that produce unusual optical signatures. Our theories of planet formation, cometary evolution, and interstellar processing need expansion. Part 11. Interstellar Objects and what 3i Atlas means. We live in a universe where objects drift between the stars like seeds on a cosmic wind, and until very recently, we had never caught one passing through. Let me put this in perspective for you. In 2017, astronomers spotted something streaking through our solar system that didn't belong here. They called it 1i/Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first. It was tumbling, cigar-shaped, or possibly flat like a pancake, and moving too fast to have originated from our sun. Then in 2019, we found 2i/Borisov, a comet from another star system that behaved exactly like our own comets, complete with a tail of gas and dust. both objects were fascinating, both were unprecedented, and both left us with more questions than answers. Now we have 3I Atlas, the third confirmed interstellar visitor in human history, and this one is playing by completely different rules. Think about that for a moment. 3 objects, 3 different personalities, 3 different ways of moving through space that tell 3 completely different stories about how planetary systems form around distant stars. Oumuamua was the weird uncle nobody could quite figure out. Borisov was the familiar cousin who reminded us of home. 3I Atlas is the guest who just walked through your front door and started rearranging your furniture. Here's what makes interstellar objects so scientifically valuable. These aren't rocks that formed in our neighborhood 4.6 billion years ago when our solar system was still a swirling disk of gas and dust. These are building blocks from completely different stellar environments, forged in the planetary nurseries of stars we can barely see, carrying chemical signatures and volatile inventories that tell us how planet formation works across the galaxy. Every interstellar object is a free sample from another star's planetary system, delivered directly to our doorstep without us having to travel trillions of kilometers to collect it. Scientists study these objects the way archaeologists study pottery shards from ancient civilizations. The composition tells you what materials were available. The structure tells you what conditions existed during formation. The volatiles, those ices and organic compounds that evaporate easily, tell you about temperature and chemistry. With Borisov, we learned that comet formation around other stars produces objects remarkably similar to our own comets. With Oumuamua, we learned that some interstellar objects can be completely unlike anything in our solar system, possibly pancake-flat chunks of nitrogen ice, or hydrogen icebergs, or something else entirely. 3I Atlas is breaking new ground in ways that should make your skin prickle. It's larger than the previous interstellar visitors. It's brighter, meaning we can actually study it in detail instead of squinting at a faint dot. It's more active, producing outbursts and changes that give us real-time data about its composition and behavior. Its perihelion, that closest approach to the Sun, brought it deeper into the solar system than Borisov ever came, exposing it to intense solar radiation and heat. And its composition, well, that's where things get truly strange. Remember those amino acids and organic compounds we discussed earlier, the ones that shouldn't survive the journey through interstellar space but somehow did? That's not how our models of interstellar objects work. Our current understanding of planet formation suggests that objects ejected from other star systems should have their surfaces scoured clean by cosmic radiation during their million-year journeys through the void. They should arrive as pristine time capsules of their original star systems, yes, but also as radiation-damaged relics with all their surface volatiles long since stripped away. 3I Atlas arrived with its organics intact, which means either it's much younger than it should be, or it was protected somehow, or our models are fundamentally wrong. The behavior is even more troubling. Natural objects don't brighten when they should dim. They don't maintain precise trajectories while producing unexplained thrust. They don't emit radio signals at frequencies that just happen to match the universal signature of hydrogen. If 3I Atlas is natural but exotic, then we need to completely revise our understanding of what kinds of objects can form around other stars and what kinds of materials can survive interstellar transit. If it's artificial, then every assumption we've ever made about our place in the universe just became obsolete. Let me paint you a picture of what each possibility means. If 3I Atlas is natural, then there are entire populations of interstellar objects we haven't previously considered. Objects that form in ways we don't understand, from materials we haven't studied, in environments we haven't modelled. This would be like discovering a new kingdom of life on Earth, something as fundamentally different from bacteria, plants and animals as all 3 are from each other. It would mean the galaxy is weirder and more diverse than we imagined, which is both exciting and humbling. If 3I Atlas is artificial, then the implications cascade outward like ripples on a pond. An artificial interstellar object means our solar system is being visited right now by probes from another civilization. It means we are not alone. It means someone else figured out how to navigate between the stars and decided we were worth investigating. It means every science fiction story about first contact suddenly becomes a blueprint instead of a fantasy. And it means we need to ask ourselves some very uncomfortable questions about whether we're ready for that conversation. The timing is almost perfect. The European Space Agency has a mission called Comet Interceptor, scheduled for the 2030s. designed specifically to intercept and study pristine comets or interstellar objects. Everything we learn from 3i Atlas, every measurement we take, every anomaly we document, will inform how we design that mission and what instruments we include. If we can figure out what makes 3i Atlas tick, we'll be better prepared to study the next interstellar visitor, and the one after that, and the one after that. The field of interstellar object science is barely 8 years old. We're infants crawling around in the dark, bumping into furniture we didn't know existed. 3i Atlas is teaching us that the universe has surprises we haven't even begun to categorize, and as we try to make sense of what this object is and where it came from, we're simultaneously watching breakthroughs in fundamental physics that might change how we interpret everything we're seeing. Part 12, Quantum and Physics, headline, Universe Not a Simulation. There's a question that's been bubbling through physics and philosophy departments for decades, and it goes like this. What if everything you see, everything you touch, everything you think you know about reality is actually just code running on some incomprehensibly advanced computer? What if the universe is a simulation and we're all just characters in someone else's video game? It sounds like the premise of a science fiction movie, and in fact it is. But it's also a genuinely debated hypothesis in theoretical physics. Recently, a team of researchers claimed to have mathematical proof that the universe is not a simulation, and the timing of that announcement is almost too perfect given what we're watching with 3i Atlas. Let me walk you through the simulation hypothesis first, because it's actually a surprisingly logical idea. The argument goes like this. If it's possible to create simulations of conscious beings, and if any civilization becomes advanced enough to create such simulations, and if they create many simulations, then, statistically speaking, there are way more simulated universes than real ones. Therefore, you're probably living in a simulation. It's called the simulation argument, proposed by philosopher Nick Bostrom in 2003, and it's been taken seriously enough that physicists have actually tried to figure out how we might test it. The tests usually involve looking for glitches or limitations that would reveal the underlying computational structure. Think of it like looking for pixelation in a video game when you zoom in too far. Some physicists have suggested looking for mathematical anomalies in the cosmic microwave background radiation, the afterglow of the Big Bang. Others have proposed experiments involving quantum mechanics, where the probabilistic nature of particle behavior might reveal computational shortcuts. The idea is that if the universe is simulated, whoever's running the simulation would need to use tricks to save processing power, and those tricks might be detectable. The recent study claiming to disprove the simulation hypothesis takes a different approach. It uses Gödelian arguments, named after mathematician Kurt Gödel, who proved that any sufficiently complex logical system contains true statements that cannot be proven within that system. The researchers argue that the complexity and self-reference inherent in conscious observation of quantum systems creates logical structures that cannot be simulated without infinite computational resources. In other words, if you're conscious and observing quantum phenomena, you can't be in a simulation because simulating your consciousness would require more computing power than could possibly exist. Now, whether that proof holds up to scrutiny is still being debated. Mathematics is full of claimed proofs that later turn out to have subtle flaws, but the very fact that we're having this conversation tells you something about where physics is right now. We're at a point where the boundary between science, philosophy and speculation has become genuinely blurry. We're asking questions that would have seemed absurd a century ago, and we're taking them seriously because our understanding of reality has become so sophisticated that we can't rule out ideas that sound completely insane. Here's where 3i Atlas enters the conversation. If we're seriously considering that this object might be artificial, that it might be an engineered probe from another civilization, then we're contemplating evidence of intelligent design in the cosmos. Not in the religious sense, but in the literal sense of something designed by intelligence. And that raises a fascinating question. If we find evidence of artificial objects in space, does that make us more or less likely to be living in a simulation? Think about it from both angles. On one hand, if we're in a simulation, maybe the simulators are populating the universe with little clues, artificial objects designed to test how we respond to first contact, scenarios. 3i Atlas could be a scripted event, a plot point in whatever story is being told with our universe. On the other hand, if we're not in a simulation, then finding an artificial interstellar probe would be evidence that the universe is even stranger and more interesting than we thought. Full of civilizations building things and sending them across the void. the philosophical implications spiral outward like fractals. Are we watching a probe from within a simulation or outside of one? If it's outside, and if we're in a simulation, then the probe itself might be real in a way we're not, existing on a higher level of reality. If we're not in a simulation, then both we and the probe are equally real, equally physical, equally subject to the laws of physics. But what would those laws be? Are the physics we observe the fundamental rules of reality, or are they emergent properties of some deeper substrate we don't understand? Consider the behavior of 3i Atlas through this lens. The unexplained acceleration, the precise trajectory adjustments, the radio signals at the hydrogen line frequency. If we're in a simulation, these could be intentional deviations from the programmed laws of physics, glitches or Easter eggs left by the simulators. If we're not in a simulation, then these behaviors suggest technology operating on principles we haven't discovered yet, which means our understanding of physics is incomplete but not fundamentally wrong. The mathematics of Gödelian incompleteness adds another layer. If consciousness creates logical structures that can't be simulated, then any civilization advanced enough to build interstellar probes would also have consciousness that can't be simulated. This means both we and the probe's creators, if it has creators, are necessarily real in the same sense. We're not characters in a video game, we're actual entities experiencing actual reality, and the probe is an actual object built by actual beings who solved actual engineering problems using actual physics. But here's the twist that should make you pause. All of this assumes that the categories we're using, simulation versus reality, artificial versus natural, make sense at the fundamental level. What if they don't? What if the universe is neither purely physical nor purely computational, but something else entirely, something we don't have words for because we've never encountered it? What if 3i Atlas is showing us that our entire framework for understanding reality needs to be rebuilt from the ground up? These are ideas, not proof. I want to be clear about that. We're in the realm of speculation here, not established science, but speculation informed by real data, real observations, real anomalies that don't fit our models. The universe is not obligated to make sense to us. It's not required to operate according to rules we find intuitive or comfortable. And as our instruments get better, as our theories get more sophisticated, as our observations push deeper into the unknown, we keep finding things that challenge our assumptions. 3i Atlas is one of those things. Whether it's a natural object that happens to mimic artificial behavior, or an actual artificial object mimicking natural behavior until it doesn't, it's forcing us to ask questions we weren't asking before. And those questions matter, because the answers will change everything. Meanwhile, the instruments we're using to study this object are themselves undergoing revolutionary changes, opening new windows onto the cosmos that might finally give us the data we need to settle these questions once and for all. Part 13, Astronomy Instrumentation. Breakthrough, neutrino detectors as colliders. There's a detector buried under a kilometre of ice at the South Pole, and it's about to change how we see the universe. It's called IceCube, and technically it's a neutrino detector, designed to catch ghostly particles that pass through the Earth like bullets through fog. But scientists have realised something remarkable. IceCube and detectors like it aren't just passive observers. They're cosmic particle colliders, natural laboratories, where high-energy particles from space slam into matter with energies we could never achieve in human-built accelerators. And this matters for 3i Atlas, because if that object is doing anything unusual, anything that involves high-energy physics or exotic propulsion, the next generation of instruments might actually be able to detect it. Let me explain what neutrinos are and why they matter. Neutrinos are subatomic particles with almost no mass and no electric charge. They're produced in nuclear reactions like the fusion happening in the core of the Sun or the decay of radioactive materials. Trillions of neutrinos pass through your body every second, but because they barely interact with normal matter, you never notice. They just zip through you, through the Earth, through everything like ghosts passing through walls. Detecting them requires enormous volumes of material and incredibly sensitive instruments, which is why IceCube is a cubic kilometre of instrumented ice. When a high-energy neutrino does interact with the ice, it produces a shower of secondary particles that emit blue light, Cherenkov radiation, which sensors detect. By analysing the pattern of light, scientists can figure out where the neutrino came from and how much energy it had. IceCube has detected neutrinos from supernova remnants, from the cores of active galaxies, from sources billions of light-years away. It's like having a telescope that looks through the Earth instead of around it, seeing parts of the universe that are blocked from optical and radio telescopes by intervening gas and dust. But here's the really cool part. When ultra-high energy cosmic rays, charged particles accelerated to nearly the speed of light by some cosmic process, hit our atmosphere or the ice, they create particle cascades with energies far beyond anything we can produce in the Large Hadron Collider. The LHC can smash protons together at 14 tera electron volts. Cosmic rays detected by IceCube can have energies of millions or billions of tera electron volts. These are cosmic colliders, and detectors like IceCube are recording the results. This opens up a new frontier in high-energy astrophysics. We can study particle physics at energies that would require building an accelerator the size of a solar system. We can look for exotic particles, test theories about dark matter, probe the structure of space-time at the smallest scales. And if 3i Atlas is producing any kind of high-energy emissions, any bursts of particles or radiation that accompany its thrust or trajectory changes, the next generation of detectors might be able to see it. Imagine this scenario. 3i Atlas fires some kind of propulsion system, maybe a fusion drive or matter-antimatter annihilation or something even more exotic. That process would produce neutrinos, gamma rays, maybe even gravitational waves if the energy output is high enough. Current instruments might miss these signals because they're faint or because they're not pointed in the right direction at the right time. But upgraded neutrino detectors with better sensitivity and better angular resolution could catch them. Gamma-ray telescopes like Fermi or the upcoming CTA, the Cherenkov Telescope Array, could detect the high-energy photons. Gravitational wave observatories like LIGO and Virgo could sense space-time ripples if the propulsion involves massive energy changes. This is multi-messenger astronomy, the idea that we should study cosmic objects using every possible signal they emit. We've already done this with spectacular success. In 2017, LIGO detected gravitational waves from 2 neutron stars merging, and within seconds, telescopes around the world were pointed at the source. They saw a kilonova, an explosion that forges heavy elements like gold and platinum. They detected gamma rays, X-rays, optical light, infrared, radio waves, every wavelength of light, plus gravitational waves, plus probably neutrinos, though those are harder to confirm. It was the most thoroughly observed cosmic event in history, and it taught us more about neutron star physics in a few hours than we'd learned in decades. Now, apply that approach to 3i Atlas. If this object is artificial, if it has propulsion, we should be able to detect multiple signatures. The visible brightening we've already seen. Radio emissions at 1.4 GHz, reportedly detected near Mars. Infrared signatures from heat. Ultraviolet emissions from ionized gases. X-rays or gamma rays from high-energy processes. Neutrinos from nuclear reactions. Gravitational waves if the propulsion involves rapid changes in mass distribution. Every signal tells a different part of the story, and combining them all gives us a complete picture of what's happening. The challenge is coordination. These instruments don't all talk to each other automatically. Astronomers have to set up alert systems so when one detector sees something interesting, others can be notified and reoriented if possible. There are networks for this now, like the Astronomer's Telegram and various automated alert systems, but they're primarily designed for transient events like supernovae and gamma-ray bursts. An interstellar object moving through the solar system is a different beast. It's not transient in the sense of lasting seconds or minutes. It's moving slowly by cosmic standards, giving us weeks or months to observe it, but it's also doing things that might require coordinated observations from multiple instruments to understand. Think about the reported radio signal at 1.4 GHz. That's the hydrogen line, the frequency at which neutral hydrogen emits and absorbs radiation, and it's considered a universal marker for communication, because any technological civilization would know about it. If that detection is real, and if it happens again, we need radio telescopes pointed at 3i Atlas continuously to catch it. Not just one telescope, but many in different locations, using different instruments, to rule out interference and confirm it's coming from the object, and not from Earth-based sources or instrumental artifacts. Meanwhile, optical telescopes should be monitoring the object's brightness and colour. Infrared telescopes should be looking for heat signatures that might indicate internal power sources. Ultraviolet and X-ray telescopes should be checking for high-energy emissions. Neutrino detectors should be running in coincidence mode, looking for bursts that correlate with visible events. It's a massive coordinated effort, and it's exactly the kind of campaign that happens for supernovae or gravitational wave sources, but never before for a solar system object that might be artificial. The instrumentation breakthroughs make this possible now in ways it wouldn't have been even 10 years ago. IceCube is getting upgraded with better sensitivity. The Cherenkov Telescope Array will be the most sensitive gamma-ray observatory ever built. New radio telescope arrays like ALMA and Meerkat have unprecedented resolution and sensitivity. Gravitational wave detectors are being improved to detect smaller ripples in space-time. We're entering an era where multi-messenger astronomy isn't just for exotic cosmic explosions. It's for anything unusual, including potentially artificial objects passing through our neighborhood. And if we do detect something definitive, some signature that screams artificial in a way that can't be explained by natural processes, then the game changes completely. Because then we're not just observing a weird object, we're observing technology. And technology has patterns, purposes, signatures that tell you about the civilization that built it. The frequency of radio transmissions might tell you about their physics understanding. The propulsion signatures might tell you about their energy sources. The trajectory might tell you about their intentions. Every data point becomes a message, intentional or not, about who they are and what they want. But even if 3i Atlas turns out to be natural, the instrumentation revolution matters, because there will be more interstellar objects. Statistics suggest we should see a few per year with current survey capabilities, and as our surveys get better, we'll see more. Each one is a new mystery, a new set of questions, a new opportunity to learn something we didn't know. And with the right instruments, coordinated observations, and multi-messenger approaches, we'll be ready to study them in ways we couldn't before. The universe is full of surprises, and we're finally building the tools to see them clearly. While we're doing that, our own solar system is keeping us plenty busy with its own set of strange behaviours and upcoming observational opportunities. Part 14. Solar System Observation and Next Windows. Our solar system is not a quiet place. Right now, as you're hearing this, there are asteroids tumbling past Earth, comets diving toward the Sun, spacecraft transmitting data from Mars and Jupiter, and the outer reaches of the system. There are telescopes scanning the sky every night, cataloguing objects, measuring trajectories, flagging anything unusual. And in November 2025, we're in the middle of a particularly interesting window of celestial activity. There was a supermoon earlier this month, the full moon at its closest approach to Earth, appearing slightly larger and brighter than usual. Surveys have flagged new near-Earth asteroids, rocks a few meters to a few hundred meters across, on trajectories that bring them uncomfortably close to our planet. And then there's 3i Atlas, barreling toward its closest approach to Earth on December 19th, 2025, giving us a precious window to observe it before it potentially vanishes forever into the outer solar system or beyond. Let me put December 19th in context for you. That date is less than 2 months away as I'm speaking these words. 3i Atlas is currently somewhere between Mars and Earth, moving at roughly 30 kilometers per second relative to the Sun, which sounds fast but in astronomical terms means it's taking weeks to cross distances that light crosses in minutes. On December 19th, it will pass about 0.9 astronomical units from Earth, roughly the distance between Earth and the Sun. That's not close in everyday terms, that's about 135 million kilometers, but in astronomical terms it's close enough for detailed observations with ground-based telescopes, close enough that we might even be able to bounce radar signals off it and measure its shape and rotation. The challenge is the Sun. 3i Atlas already passed Perihelion on October 29th, when it was closest to the Sun and therefore hardest to observe from Earth because it was in nearly the same direction as the blinding solar disk. Astronomers call this solar conjunction, and it's a nightmare for observations. You can't point telescopes directly at the Sun without specialized equipment and filters, and even then, you're fighting glare and atmospheric distortion. As the object moves away from perihelion and toward Earth, it gets easier to see, but there's still a window where it's too close to the Sun in the sky to observe safely. That window is closing now. By mid-November, 3i Atlas should be far enough from the Sun's glare that major observatories can start dedicated observing campaigns. Telescopes in Chile, Hawaii, the Canary Islands, Arizona, all the major astronomical sites around the world, will be turning their attention to this object. They'll be measuring its brightness, tracking changes in colour, looking for signs of outbursting or fading, analysing the spectrum of light it reflects and emits to determine composition and activity. radio telescopes are particularly interesting. The reported detection of 1.4 GHz signals near Mars weeks ago, if real, suggests that radio observations might reveal more than optical ones. Facilities like the Very Large Array in New Mexico, ALMA in Chile, the Arecibo replacement if it's operational by then, these could all be tasked to listen for emissions from 3i Atlas. Radio astronomy doesn't care about daylight or weather. You can observe 24/7 if the object is above the horizon. And if there are periodic signals, regular pulses or patterns that suggest artificial origin, radio telescopes are the instruments that will find them. There's also the possibility of spacecraft observations. We have orbiters around Mars, including the Mars Reconnaissance Orbiter and the European Space Agency's Mars Express. These spacecraft have cameras and instruments that could, in principle, be pointed at 3i Atlas if it passes close enough to Mars or if mission controllers decide it's worth the effort. The challenge is that these spacecraft are designed to study Mars, not interstellar objects. Retasking them requires planning, approval, and sacrificing other scientific observations. But if 3i Atlas is as anomalous as it appears, the case for spacecraft observations becomes compelling. Ground-based radar is another option. Facilities like the Goldstone Deep Space Network antenna in California can transmit radio waves at passing asteroids and comets and measure the reflected signal. Radar observations can determine an object's size, shape, rotation rate, and surface properties with incredible precision. They can even detect surface features, like craters or boulders, by analysing how the radar echo changes over time. If 3i Atlas has any unusual structures, any artificial-looking components, radar might reveal them, but there are limitations. Radar range is limited by power and sensitivity. The signal weakens with the fourth power of distance, meaning if you double the distance, the returning signal is 16 times weaker. For 3i Atlas, at its closest approach, we're talking about distances where radar is right at the edge of feasibility. It might work or it might not, depending on the object's size and how reflective its surface is to radio waves. If the surface is icy and smooth, radar will bounce off well. If it's rough and absorptive, the signal might be too weak to detect. What should we be watching for? There's a list. Changes in brightness that don't correlate with distance from the Sun or Earth, which would suggest internal activity or controlled maneuvering. Changes in colour, shifts in the spectrum that indicate composition changes or temperature variations. Signs of acceleration or course changes that can't be explained by gravitational interactions with the Sun and planets. Radio emissions, especially at frequencies like 1.4 GHz that suggest intelligent intent. Unusual tail behaviour, if the object has a tail, like jets pointing in directions inconsistent with solar pressure or rotation. Anything that deviates from the boring, predictable behaviour of normal comets and asteroids. There's also the possibility that 3i Atlas does nothing unusual during this window, that it fades as it moves away from the Sun, following a predictable light curve, emitting no signals, showing no thrust, behaving exactly like a normal comet. If that happens, it doesn't mean the earlier anomalies weren't real. It means either the activity was temporary, tied to perihelion passage and intense solar heating, or the object has gone dormant, conserving energy or waiting for some other trigger. Or it means we're misinterpreting the data, seeing patterns in noise, and the whole artificial hypothesis is wrong. That's the scientific process. You make observations, form hypotheses, make predictions, test those predictions with new observations. If the predictions pan out, the hypothesis gains strength. If they don't, you revise or discard the hypothesis. Right now, we're in the testing phase. December 19th is the exam date. Either 3i Atlas continues to defy natural explanations, or it doesn't. Either we get data that pushes us decisively toward one conclusion or the other, or we remain in ambiguity, uncertain, and frustrated. Amateur astronomers and citizen scientists can participate in this, by the way. You don't need a professional telescope to contribute. 3i Atlas should be visible in moderately sized amateur telescopes, maybe even binoculars if it brightens enough, and there are networks of amateur observers who coordinate to track comets and asteroids. Websites like the Sky Live provide real-time positions and tracking information. You can point your telescope at the coordinates, take images, measure brightness, and submit your data to databases where professional astronomers can access it. Citizen science has discovered supernovae, found new asteroids, contributed to our understanding of variable stars. There's no reason it can't help with 3i Atlas too. The next 2 months are critical. This is the window where we'll learn the most about this object, where we'll gather the data that might answer the biggest question humanity has ever asked. Are we alone? And if we're not, is this our first confirmed encounter with evidence of extraterrestrial technology? The telescopes are ready, the instruments are calibrated, the observing schedules are being drawn up. All we can do now is watch and wait, and hope the universe decides to reveal a little more of its secrets before this object moves beyond our reach. Part 15. What's next? And call to action. So here we are. 3i Atlas has passed perihelion, performed manoeuvres that shouldn't be possible for a natural object, brightened when physics says it should have dimmed, and is now moving toward Earth while astronomers scramble to figure out what the hell they're looking at. We've walked through the data, examined the hypotheses, confronted the uncomfortable reality that both possible explanations, natural or artificial, are extraordinary in their own ways, and now we're at the point where speculation has to give way to concrete observations, where philosophy has to yield to measurement, where the question, what is this thing, demands an answer based on evidence, not wishful thinking or fear. Let me summarize where we stand. 3i Atlas did things we didn't expect. It survived perihelion passage at 0.38 astronomical units from the Sun, closer than Mercury's orbit, where temperatures should have vaporized conventional ices and blasted away volatiles. It produced outbursts and brightness changes that don't match any known cometary behavior. It accelerated in ways that require thrust, sustained force pushing it off a gravitational trajectory, without showing the expected gas and dust emissions that would accompany natural outgassing. It maintained a trajectory so precise that small deviations would make the difference between interesting comet and impossible object, and those deviations stayed within margins that suggest control, not chaos. And there are reports, unconfirmed but persistent, of radio emissions at 1.4 GHz, the hydrogen line, detected near Mars weeks before perihelion. Either this is the most statistically improbable natural event in the history of cosmic observations, a confluence of coincidences so unlikely that we should question whether probability even means what we think it means, or it's artificial. Those are the options. There's no middle ground that makes sense. Natural objects follow rules. They obey gravity, thermodynamics, conservation of momentum. They don't make precise course corrections without visible exhaust. They don't emit signals at frequencies chosen specifically to announce, "Here I am," to anyone listening. If 3i Atlas is natural, then everything we think we know about comets, asteroids, interstellar objects, and the statistical distribution of compositions and behaviors in the galaxy needs to be thrown out and rebuilt from scratch. If it's artificial, then humanity just witnessed first contact. Not the Hollywood version with ships landing on the White House lawn and aliens stepping out to deliver speeches. The quiet version. The version where an intelligently guided probe from another star system enters our solar system, performs observations or sample collection or whatever its mission is, and departs, leaving us to piece together what happened from fragmentary data and confused observations. That's what first contact probably looks like in reality. Not dramatic, not obvious. Just strange enough that we notice, not clear enough that we can be certain. The near-term forecast is straightforward. December 19th, 2025, closest approach to Earth at 0.9 astronomical units. That's less than 2 months away. Between now and then, every major observatory on the planet should be pointing instruments at this object. Ground-based optical and infrared telescopes, radio arrays, radar facilities, spacecraft with cameras and spectrometers. The data collected during this window will either confirm the anomalies or explain them away. We'll measure brightness curves, color changes, spectral signatures, trajectory deviations, potential radio emissions. We'll analyze, compare, model, simulate, and at the end of it, we'll know more than we do now. What data would push us decisively toward one conclusion or the other? For the artificial hypothesis, we'd need something unambiguous. Persistent radio transmissions with structure, patterns, modulation that can't be natural. Visible propulsion, jets of plasma or light, or something else emerging from the object in directions that correlate with trajectory changes. Detection of manufactured materials, alloys or composites with isotopic ratios that don't occur naturally. Geometric shapes, surface features too regular to be coincidental. Any of these would be smoking guns, evidence that couldn't be explained by natural processes no matter how exotic. For the natural hypothesis, we'd need conventional explanations for the anomalies. Discovery that the object is made of some unusual but still natural material that sublimates asymmetrically, producing thrust without visible outgassing. Confirmation that the radio signals were instrumental artifacts or Earth-based interference. Trajectory analysis showing the deviations are within margins explainable by modelling uncertainties and gravitational perturbations from planets. Brightness changes consistent with rotation and uneven surface albedo. Nothing impossible, nothing requiring. Technology, just a really weird comet that happens to mimic artificial behaviour. Right now, we don't have enough data to be certain either way. That's the frustrating truth. We're in the middle of the story, not at the end, and the ending hasn't been written yet. But you can follow along. There are tools for that. The Sky Live and similar websites provide real-time tracking data for 3i Atlas. You can see where it is in the sky, what constellation it's passing through, whether it's above the horizon from your location. If you have a telescope, you can observe it yourself, take images, measure its brightness, contribute to the citizen science effort. If you don't have a telescope, you can follow observing reports from professionals and amateurs, read updates on astronomy forums and social media, watch for press releases from major observatories. This is not a passive experience. Astronomy is one of the last sciences where amateurs can make genuine contributions, where your backyard telescope can collect data that matters, where your observations might catch something the professionals missed because they were pointed in the wrong direction at the wrong time. If 3i Atlas does something spectacular, something undeniably artificial, you could be one of the first to see it. And even if it doesn't, even if it turns out to be a very weird but still natural object, you'll have participated in the scientific process, contributed to our collective understanding of what's out there. But let's talk about the bigger question. If this is an engineered object, if there's another civilization out there advanced enough to send probes across interstellar distances, what does that mean for humanity? Are we ready for that knowledge? Are our institutions, our governments, our philosophies prepared to incorporate the reality of extraterrestrial intelligence into how we see ourselves and our place in the universe? Do we even have protocols for this? The answer is sort of. There's something called the SETI protocols, guidelines developed by the Search for Extraterrestrial Intelligence community for what to do if we detect a signal from another civilization. They include steps like verifying the signal, ruling out natural and human-made sources, notifying the scientific community, and eventually informing the public and relevant authorities. But those protocols were written with radio signals in mind, long-distance transmissions across light years, not physical objects moving through our solar system. 3i Atlas, if artificial, is a different category entirely. It's not a message, it's a presence, and the protocols for how to respond to a physical probe, whether to attempt communication, whether to approach it, whether to even acknowledge that we've noticed it, those protocols barely exist. Some scientists argue we should be cautious. If there's a probe in our solar system, it's observing us, and anything we do in response is being recorded and analysed. Our reaction tells them something about our technological level, our social organisation, our decision-making processes. Do we respond with curiosity or fear? Do we coordinate internationally or act as competing nations? Do we try to communicate or do we stay silent, hoping it goes away? Every choice we make is a message, whether we intend it or not. Others argue we should be bold. If another civilization went to the trouble of sending a probe across interstellar space, they're expecting to be noticed eventually. Staying silent doesn't hide us. We've been broadcasting radio and television signals into space for decades. Our atmospheric composition, the oxygen and methane signatures that indicate biological activity, are visible to any civilization with telescopes sensitive enough to analyze exoplanet atmospheres. They know we're here. Playing coy at this point is pointless. We should try to communicate, transmit signals at the hydrogen line frequency or other universal markers, make it clear we're intelligent and interested in contact. The truth is, nobody knows what the right answer is because we've never been in this situation before. Every previous claim of artificial objects or alien signals has turned out to be misidentified natural phenomena or hoaxes. Oumuamua was weird enough to generate speculation about artificial origin, but the consensus eventually settled on exotic natural explanations, nitrogen icebergs or hydrogen ice flows or fragmented planetesimals. The WOW signal from 1977, a strong narrowband radio signal detected by the Big Ear telescope that matched the hydrogen line, was never detected again and remains unexplained but is generally assumed to be some kind of terrestrial or instrumental artifact. We've never had unambiguous evidence of extraterrestrial technology. 3i Atlas might be the first, or it might be the latest in a long line of false alarms. But here's what makes this different. The data is getting better. The observations are more numerous, more precise, more difficult to dismiss as instrumental errors or misinterpretations. The anomalies are piling up instead of being explained away, and the object is still here, still observable, still doing things that challenge our understanding. This isn't a one-time signal that vanished before anyone could verify it. This is an ongoing event, a slow-motion revelation that's giving us time to study it, question it, test hypotheses against new data. If 3i Atlas is artificial, we're watching the most important discovery in human history unfold in real time. If it's natural, we're watching the most bizarre natural phenomenon ever recorded. Either way, we're witnessing something profound. So what should you do? First, stay informed. Follow the observations. Read the updates. Understand that this situation is evolving and that what we know today might be contradicted by data collected tomorrow. Science is a process, not a destination, and the process requires patience and willingness to change your mind when new evidence appears. Second, if you have the means, observe it yourself. Get involved in citizen science. Contribute data. Be part of the collective effort to understand what's happening. Third, think about what it means, not just scientifically but philosophically, emotionally, practically. If we're not alone, how does that change your perspective on humanity's future, on our conflicts and challenges, on the meaning of existence? And fourth, talk about it. This isn't something that should be kept in academic journals and specialist forums. This is a story that belongs to everyone, because if there's another civilization out there, that fact affects everyone. The implications ripple through every aspect of human culture: religion, philosophy, politics, economics, art, literature, science. We need to have conversations about what we're seeing and what it might mean, conversations that include diverse perspectives and voices, not just astronomers and physicists, but ethicists and theologians and poets and farmers and teachers and everyone else who has a stake in humanity's future. Eyes on the skies, because the universe just may be sending us a message. Not a message in the sense of words or pictures transmitted across space, but a message in the sense of an object, a physical presence, a thing that exists and moves and behaves in ways that force us to question our assumptions. 3i Atlas is either a cosmic accident so improbable it shouldn't exist, or it's a deliberate artifact from another mind, another civilization, another way of being intelligent in the universe. Both possibilities are staggering. Both require us to expand our understanding of what's possible. If this turns out to be the most improbable natural event in cosmic history, is that still the most extraordinary story ever told? I think it is. Because it means the universe is capable of producing coincidences so unlikely, so precisely tuned to mimic intelligence, that we can't distinguish them from actual intelligence even with our best instruments and most sophisticated models. It means randomness can sculpt objects and trajectories and behaviors that look designed, that feel designed, but aren't. It means the cosmos is stranger and more creative than we imagined, capable of generating phenomena that push right up against the boundary of the impossible without quite crossing it. And if it's artificial, then we're living through first contact, quiet, ambiguous, probably deniable for anyone who wants to deny it, but real nonetheless. We're watching a probe from another star system move through ours, carrying out whatever mission it was sent to perform, probably indifferent to whether we notice or care. With the ants watching the human walk through the forest, barely comprehending what we're seeing, certainly not understanding the intentions or technology involved, but aware enough to know that something significant just happened. Either way, we're not the same species we were before 3i Atlas entered our solar system. We've seen something that changes the equation. We've been confronted with evidence that our place in the universe is either far stranger than we thought, if the object is natural, or far less lonely than we hoped and feared, if it's artificial. The next few months will bring more data, more observations, more opportunities to narrow down the possibilities. December 19th is coming. The closest approach. The moment when we'll have our best chance to see this object clearly and understand what it is. And after that, if it's natural, we'll watch it fade into the distance, carrying its mysteries with it, leaving us to argue about interpretations and wait for the next interstellar visitor to give us another chance to solve the puzzle. If it's artificial, well, then the story is just beginning. Because one probe means there are others. One civilization sending objects across interstellar space means the galaxy is populated, active, full of entities doing things, building things, exploring. It means we're part of something larger, a community of minds scattered across the stars, each solving the same problems of survival and curiosity and meaning in their own ways. The universe doesn't owe us answers. It doesn't care whether we understand it or not. But we care. We're the species that looks up at the night sky and asks why, asks how, asks what's out there and whether we're alone. 3i Atlas is forcing us to confront those questions with new urgency, new data, new possibilities, and whatever the answer turns out to be, whatever we learn in the coming months, will be different for having asked the question seriously and looked for the answer honestly. So keep watching, keep questioning, keep your mind open to possibilities that seem absurd until they're proven real. The universe is under no obligation to match your intuitions or comfort your fears. It's vast and ancient and full of phenomena we haven't categorized yet, processes we haven't named, objects we haven't imagined. 3i Atlas is one of those objects, and whether it's the most impossible natural phenomenon or the most momentous artificial one, it's here, it's real, and it's teaching us that the cosmos still has surprises left to spring on us. This is the moment. This is the window. Eyes on the skies, data in hand, telescopes pointed, instruments recording. Something is moving through our solar system that doesn't make sense, and making sense of it might just be the most important thing our species has ever done. Because if we're not alone, everything changes. And if we are alone, if this incredible object is just the universe being weird in ways we didn't predict, well, that's its own kind of miracle. Either way, we're watching history unfold, one observation at a time, one data point closer to the truth. And the truth, whatever it is out there waiting for us to find it.